And now we are ready to find out what a standard normal distribution is. And so at this point, learning about a general normal distribution, and even though we didn't get too far on a normal distribution, on any general normal distribution, but so keep in mind, being a normal distribution, generally it's a bell curve and has a symbolic statement n with some mu and with some sigma. And so you can now realize that there are plenty of normal distributions out there as long as you have a bell curve data shape, distribution shape, and you have a known mu and you got a known sigma for standard deviation. That is a bell curve. That is a normal distribution. And so among many different normal distributions out there, then the standard normal distribution is specifically the N01. So this is my most simple definition. The standard normal distribution is the N01. And so here's how to make sense out of it. As the name suggests, it's called a standard normal distribution. So first requirement, it has to be a normal distribution. And that's why it has that being an N with some mean and some standard deviation. And now being a standard, the next requirement now is that bell curve needs to have mean center at 0 and standard deviation being precisely 1. And that's why we have this. For short, an N01. And that's how I call it's the name of the. So what we have here is the standard normal distribution. And now we have another special requirement in addition to being a bell curve and center at 0 and standard deviation 1. We have another special requirement that anytime you are working with a standard normal distribution or anytime we are communicating with other statisticians to indicate a standard normal distribution, make sure we use the capital letter Z to name the random variable. So Z is the reserved. How's that? So the special capital letter Z is reserved to name the random variable on the standard normal distribution. And for that reason, consequently, as a formal symbolic statement to represent, to describe, we have a standard normal distribution data, then we're looking at this statement symbolically Z that is normally distributed on a bell curve at mean 0, standard deviation 1. And this is a complete description of the standard normal distribution. The random variable's name is Z, and Z is some data, some population data, continuous random variable that's being distributed on a normal distribution at mean 0 in the center and standard deviation 1. And now it's just a little bit of my own notation, convenient to communicate throughout the rest of this video and many other videos later on in a quarter here in the statistic class here that we're taking. But generally, a lot of time you might see me regard to as an S and D right here for being a standard normal distribution. So that's another notation of my own that I use. I feel quite convenient to use it that way. An S and D, a lot of time when you hear I call an S and D, it's also mean a standard normal distribution. But so I really need to emphasize this as throughout my time teaching statistics, I keep having students mistakenly the standard normal distribution with some other normal distribution that almost looks like a standard normal distribution. So really an N01 or a standard normal distribution has really three critical requirements. So first of all, it has to be a bell curve. So it has to be a bell curve. This symbol means bell curve, bell-shaped curve, but also require that the mean is precisely given at 0, and standard deviation is required to be given to be 1. And so the shape of the distribution, this is shape of the distribution, is an N being a bell curve, center, the next requirement, center at 0. So make sure we have that requirement being checked as well. And standard deviation represents spreading. So average spreading is 1. So we always have the three pieces of information, three important required pieces of information together or making up our standard normal distribution. So sometimes deceivingly we can have something like this, an N1 and 0.01. Looking close enough, but this is not a normal not the standard normal distribution, not the SND. This has a mean at 0 and a bell curve setting, but since standard deviation fails being 1, this is not the SND. And only when we are on the bell curve normal distribution, bell curve center at 0 and standard deviation 1. This is where we have, this is the SND. Okay, so now to have a better understanding about the motivation or the reason why the standard normal distribution was developed, then let me bring everybody into this little example right here. So for now, let's just take all we understand. A standard normal distribution is simply an N01, and it's just as a definition, it's just one, like back in my beginning definition, a standard normal distribution is simply a one among the many other distributions out there where the mean here is precisely at 0 or given to be 0, and the standard deviation given to be 1. And of course we have a bell curve shape data distribution or probability distribution. And so let me bring up this little example here. Let's say in this example we are once again given that we are working on on an N01. And so immediately, once again, I highly recommend getting into that habit that anytime we are instructed that we're given a bell curve data probability distribution, then have for yourself the picture of a bell curve. But here it's an SND, it's a standard normal distribution, so do not use any letter other than Z, use Z. And so the center here is now famously known to be 0, and standard deviation equals 1. And so in this problem, I'm going to furthermore say we're going to pick a value. So for now, just simply treat Z as just the special variable that we use to name any of the value on this line here, from the left to the right-hand side of the center on the bell curve. So let's say when Z equals a value, let's take Z equals, how about out of my mind right now, out of my own creativity, 1.25 right here. So right now Z is a value 1.25, so Z is a data as a random variable, and right now Z takes value equals 1.25. So my question here is, let's find the Z score of Z. Okay, so Z score of Z. And so this z value currently is given to be 1.25. And how do we find z score? So the last time we learned that so z score on any data, once we had the mean, so z score here is being 1.25 is our value here is currently being 1.25, and to find z score here, I must take our value, subtract the mean value being 0, and divide it by standard deviation 1. Remind yourself, so if you have any value, say namely x, finding z score of x, we're going to take value, subtract the mean, and divide it by the standard deviation sigma, and that's how we come up with z score. And this is a lowercase value as a reminder. And so in that same way, so if I'm treating here my capital Z here as a value on this bell curve, it's a data. It's the special data having mean at 0 and standard deviation 1. So as it turns out now, when we find the z score for this value of our data, 1.25, then it turns out the z score is also 1.25. So that's the connection right here. The whole intention of this standard normal distribution is so the standard normal distribution is the distribution of the z scores. So it is the distribution of z score. And what's special about those z score? Of z score from a normally distributed random variable x. And let me spend a little bit of time explaining what those statements mean right here. But it's just simply, for now, it's another way of understanding where the standard normal distribution come from, and what was that beginning motivation of why we have that development of the standard normal distribution. So now recall that finding the z score to any data value in a population can be simply done by taking the value and subtract the mean, the population mean, and divide by the standard deviation. And so the impact of this formula now is that, thinking as a larger, bigger impact here, then every value x in the population has a z score. And so a further impact is that, so now every value x in any population has a z score. And so another impact, we can see that if random variable x represents a population, then there must be a population of z scores, and we name the variable for that population capital Z, corresponding to x. And corresponding here, I mean, as far as the population size, in theory being as large, the population of the z score here is being as large as the population of x right here. And so every population has a corresponding z-score population, because every value x in that population can have an equivalent z-score. And so taking from that understanding, then back to the statement that I wrote earlier, the standard normal distribution is the distribution of z-scores from a normally distributed random variable x. What this statement means is that if some random variable x is known to be normally distributed with some mean mu and sigma and standard deviation sigma, so this is known. So if we know that some populations x is being normally distributed with mean mu and standard deviation sigma, then it must be for sure that all the z-score population coming out from this x population must also be a normal distribution. And furthermore, that normal distribution here is center at 0, mean 0, and standard deviation 1. And this population of z-score right here is known as the standard normal distribution. And so after a lot of explanations, standard normal distribution, or the N01, or even more formally, the random variable representing the z population, is normally distributed by a normal distribution with a mean value at 0 and standard deviation 1. In the end, that random variable z must be a continuous random variable again. And so being a continuous random variable, then this standard normal distribution, or this z continuous random variable, must carry all that characteristics of being a continuous random variable. And my intention here, my aim here, is to explain again that, so now even though we're in a nice smooth bell curve, and this curve here is called a PDC of all the z values of the z variables, center here now known to be at 0, and then this PDC, this standard normal distribution, has a sigma 1 standard deviation, population standard deviation being 1. But in the end, being a continuous random variable automatically makes it true that the accumulated area inside this PDC, inside this distribution, probability distribution, must be cumulatively 100%. So all that area here, because remember in the concept, now when we're looking at the continuous random variable, accumulated area is the total probability. So this total area equals 100%, because that represents all data, because all data is being represented. Right there. But also thinking of that area here as the total accumulated probability being on a bell curve, then it also means the total probability must be always equals 1. So two ways of thinking about that. And further, let's say again, let z be a random variable that's being on the bell curve centering at 0 and standard deviation 1. Or in other words, this is the standard normal distribution. Then on that nice symmetric bell curve with center right at 0, then once again, if we pick a z value, let's say if z equals a, at our level, being the introductory level of statistics, then we are not able to answer this question. Find the probability where our random variable z equals precisely a z value. So we must ignore this question. And instead, we can answer the question where find the probability on this nice z curve or nice standard normal distribution curve where our z value takes place inside an interval anywhere from a to b. So this kind of question can be answered. And graphically speaking, this question here, finding the probability in the events that our random variable takes place inside an interval. Then we can picture that we have an interval from a to b on the z-axis here. Then that probability is how much shaded area cumulatively inside of our interval from a to b on this PDC for the standard normal distribution. And this special curve, we already knew that mean is 0 and sigma being 1. And so now, quickly, I can bring up a simple example here. Let's say we're now given an n01, meaning we're on the standard normal distribution. Then once again, immediately let's draw for ourselves a nice symmetric bell curve here, but the variable's name on the horizontal axis here is the z variable. And so it's indicated that the center is 0, right in the middle. Mean value, standard deviation is 1. And so on this bell curve, once again, we already knew that the total accumulated area inside of this bell curve is 1 or 100% of area. Then the question can be asked here is that we want to find the probability where we have a z value or a z-score. Now we can now legally start thinking of the value of z as a z-score, having a z-score being less than or equal to 0. Having a z-score being less than or equal to 0, this is an interval of value, and graphically speaking, it produces a shading to the left-hand side of my mean value in the center. And so this area now I'm shading is exactly one half side of the entire area inside a bell curve. So now this answer here, without any need to do special math here, it's just simply 50%. So the probability that our z value takes place less than or equal to 0 is 50%. Now formally in probability term, we are using decimal answer. So 0.5 is again our final legitimate answer right here. And then similarly again, we can also see that an equivalent, a similar question can be brought up that what if we find a probability where our z-score or z value of this random variable being greater than or equal to 0? Then in a different shading, then this amount, this interval z greater than or equal to 0 represents anywhere being to the right hand side. And so this part to the right hand side of my mean value on the z curve, on the standard normal distribution curve, is the other 50%. So there's 50% here, and there's the other 50% being here. And I'm not talking about the length, how long this line horizontally is, but I'm talking about how much area cumulatively here. So this red area shaded is exactly half of the total amount of area being 100. And so this probability that z greater than or equal to 0 is, needless to think, 50%, or once again informal probability expression, 0.5.